All right. Hello, everyone. Today we're going to start the next unit, oxidation and reduction reactions. So we'll get into what all those mean and what the definitions of those terms are as we go through the unit. But today we just want to start with one key skill that you need to be able to do, which is assign oxidation numbers. So we've used these numbers before, but we'll kind of see how that ties in with this as we go. So what do you want to remember about these oxidation numbers? So how have we used them before? So we've used them when we're assigning charges for ionic compounds, when we do the crisscross, when we gain or lose electrons, how many electrons are lost, how many are gained, and then what's the charge of the resulting ion. But it doesn't necessarily have to be an ion. So if you look at the top bullet here on your fill-in notes, it's not an actual charge. So it doesn't have to be a charge. It can be, but it doesn't have to be. So we'll see how that pans out as we go through this stuff. So what are these oxidation numbers? What we like to say is that they're a way of keeping track of the electrons lost or gained by atoms or ions in a reaction. So what do I mean by it's not an actual charge? So here's an example. Let's say I have NaCl versus water, H2O. So remember what happens when sodium and chlorine form a compound. This is a metal, nonmetal. So we're going to get an ionic compound. So Na loses its one valence electron to become a +1 ion. And then chlorine, remember, initially has 7 valence electrons. And then it gains one more to fill its valence shell, becoming a -1 ion. All right, so this is an ionic compound. Metals lose, nonmetals gain. We have that transfer of electrons. Remember our keyword, transfer. And then H2O, nonmetal. This is covalent. So our keyword here, remember, is sharing. So here's our oxygen. Here's our shared pair. And then if you remember your CNOF table, oxygen is going to form 2 bonds and get 2 lone pairs. So even though we don't have charge formation here, transfer of electrons, we have a sharing of electrons, we're still going to use these oxidation numbers to keep track of where these electrons are going. Okay? So just keep that in mind. Doesn't matter whether it's ionic or covalent. Okay? So how do we assign these oxidation numbers? So this is the first skill you want to be able to do before we can go any further in this unit. So we're going to focus on that in this lesson, just being able to assign oxidation numbers to the elements in a compound. If you can do that, you're off to a good start. So rule number 1, the oxidation number of an uncombined element is 0. All right? So that's pretty simple because we've learned since the beginning of the year, atoms are always neutral, right? Their charge is 0. So if an element's all alone, it's going to be 0. Let's look at some examples. Magnesium. So if magnesium's all alone, you see it, solid S, right? The oxidation number is 0. So where would you write that? It would go in the top right corner, where we would normally write the charge. That's where we're going to put our oxidation state. Now look at chlorine now. Right? Chlorine, its oxidation number is also 0 because it's all alone, even though it's 2 stuck together. So the 0 goes in the top right. So don't forget about your Brinkelhoffs, those diatomic elements. Even when they're 2 stuck together, when they're in their elemental state, they're all alone. So these guys, we still consider them all alone. So if we see them by themselves, like chlorine here, it's still going to be an oxidation state of 0 because we consider that alone. Remember, the definition of a compound is 2 or more different elements chemically combined. So even though they're 2 stuck together, it's still considered its elemental state. So this is an important rule. You forget this, you're going to make a lot of mistakes moving forward in this unit. So when you see an element all alone, it gets a 0, right? Think about atoms are neutral. They're not going to have a charge, so we give them a 0, right? So step 2. What about an ion? That's pretty easy, right? This is if you have an ion in the reaction, then the oxidation number is equal to its charge. Simple. So if we have an Mg plus 2 ion, that plus 2 is going to be given to you. You're not adding that in. Then that means the oxidation number is plus 2. If you have a chloride ion, then the oxidation number is its charge. Pretty simple, right? So that's rule number 2. All right, so let's move on to rule number 3. So now this deals with assigning oxidation numbers for bonded elements. So what does it mean if we're a bonded element? What that means is we're compounds. So now we've formed compounds. So these rules only apply to compounds. So atoms of 2 or more different elements chemically combine. So don't confuse this with your uncombined elements or your ions where the charge is given, which is the oxidation state. So these are for when we have compounds, 2 or more different elements chemically combined. And this is where you're going to do the majority of your work here. So let's go through these rules, these sub-rules here to help you along. So group 1 elements are always plus 1. So that kind of makes sense. That kind of makes sense because they're in the first group. And if we remember what that means, being in the first group, you have 1 valence electron. So those group 1 elements are going to lose that 1 electron to become plus 1 ions. So the group 2 elements are always plus 2. Same reason, they're going to lose 2 electrons from their valence shell and become plus 2 ions. All right, fluorine, if you remember where fluorine is on our periodic table, it's group 17. So it wants to gain 1 electron. So it's going to become a minus 1 ion. All right, so now the next 2 are usuallys. So we'll talk about that in a little bit. But hydrogen is usually plus 1 and oxygen is usually minus 2. So you want to keep these things in mind, and you're going to use what you know to figure out what you don't know. And I'll show you what that means when we do some practice problems. So there's a little addition I'd like to add on to fluorine's rule. So for the other elements in group 17, they're not always minus 1, but sometimes they are. So here's a easy way to figure that out. If they're on the end of a compound, like this here, see how chlorine's on the end of the compound? They're going to be minus 1. But if they're on the inside of the compound, in the middle, like here, then you got to figure it out. So you're going to use what you know to figure out what you don't know. And this is where the rules come in. All right, now another rule here, because there's obviously more elements than just the ones that are listed up here, is to use the periodic table. Right? So use the periodic table to help you out. So what do I mean by that? Well, if an element only has 1 charge, you can most likely use that to help you out. If it only has 1 oxidation state, you can use that. So like aluminum here, right? Aluminum has a charge of plus 3. We don't have a rule for aluminum, but it has 1 oxidation state in the top right. So we're probably pretty safe to use that if we're trying to figure out the oxidation states of all the elements in a compound. All right, same thing for a lot of these other guys. Let me zoom in a little bit. So like zinc over here, plus 2, only has 1 choice. So we can probably use that to figure out our oxidation states of our other elements. Silver is plus 1, right? So these are some things that are going to help you as we go through. So if they only have 1 oxidation state, most likely you can use that. So, and also what you want to remember is the rules that we just went over are expressed right here on the periodic table. So what did we go over? We said group 1s are always plus 1. So look in the top right here. All of the group 1 elements have plus 1 oxidation states. Group 2s, always plus 2. Look up here, plus 2, right? Fluorine, always minus 1. There's your plus 1, your minus 1, I mean. Oxygen, usually minus 2. There's your plus 2. Hydrogens, usually plus 1. There's your plus 1, right? So it's all right there. And you can use that to help you. Okay, and then the ones, like I said, if they only have 1 choice, you can go with it. So go beyond the rules that we went over and just basically use the periodic table. All the rules are right in front of you on the periodic table. So the other halogens are usually minus 1. Look in the top, minus 1, minus 1, minus 1. Yeah, there's other oxidation states, So you're going to have to figure these guys out sometimes. But if they're on the end, like I said, of the compound, then it's going to be the -1 because they want to gain that 1 electron to fill their valence shell. All right. Okay, so let's move on to rule number 4. So how do we know how to figure out the oxidation states of the elements that we don't know in a compound? So remember, we're dealing with compounds here. Two or more different elements chemically combine. Well, just like in math, if we're trying to solve for an unknown, there can only be one unknown. So it's the same thing here. If you have more than one unknown, then there's another one that you know that you're just not seeing. So take a look at your periodic table, think about your rules. What are you missing? So what do these all have to add up to? They all have to add up to 0. And again, that makes sense because compounds are always neutral. So the sum of all the oxidation states should add up to 0. So sum of all oxidation numbers in a compound must equal 0. So what do I mean by that? So let's look at water. So what I like to do is make a little table. Break up the compound by elements, and the bottom and the top are going to be for different. All right, so what I like to do is break these up into. What I like to do is make a table. So draw the table right over the compound. So you break it up by element, and the top is for your oxidation number, which is just for one atom. Okay. So oxidation states are always per individual atom. And the bottom is going to be for our total for each element. So that's going to incorporate our subscripts. How many total atoms are in the compound, and what does that charge equal? All right, so keep this in mind. Totals on the bottom, individual oxidation numbers go on the top. So this is what we want up here. This is going to be our final answers, right? So again, what do? I use what I know to figure out what I don't know. Well, first, remember, it's got to add up to 0. So we're going to use that to figure out our unknowns. So what do I know? Well, I know oxygen is usually -2. How many oxygens are there? Remember, nothing means 1. So think of it as you're kind of multiplying on your way down. -2 times 1 is -2. So what do I need to equal 0? Well, the hydrogens have to add up to +2. It's +2 -2, 0. What does each hydrogen get? So if I have a total charge of +2 and there are 2 hydrogens, I have to distribute this charge among all of those hydrogens. So think about it as you divide your way back up, right? So you multiply your way down and you divide your way back up using your charges and the subscripts. So +2 divided by the 2 hydrogens means each hydrogen gets a +1. Okay, so this is your answer. Every element needs an oxidation state. So don't forget, don't just get the bottom to equal 0. Finish things out and give each element an individual oxidation state. Right? Why is this important? Because these numbers are what you're going to use when we move on in this unit. Okay, so you have to be able to do this and to do it well. So, and notice, right, these don't add up to 0 because it's per individual atom. The bottom is what has to add up to 0. All sum of all the oxidation states has to be 0. All right, so remember, think about it as we're multiplying on our way down, incorporating our subscripts into our calculation, and then we're dividing on the way up. So let's look at another example, CuF2. So again, use what you know to figure out what you don't know. So we know fluorine is usually -1. So what's my total? Well, -1 times 2 is -2. So what do I need to get to 0? +2. It's got to add up to 0. So there's only one copper, so it gets the whole thing. So think about it as +2 divided by 1 is +2. So copper gets the +2. So we're done. So every element needs an oxidation state before you can move on. That's how you know when you're done. So just keep that in mind. So now the next one, we have 3 elements. So no big deal. Just break it up into 3 columns, totals on the bottom, individual oxidation states on top, and use what you know to figure out what you don't know. So again, it's got to add up to 0. And what do we know? Well, I know oxygen is usually -2. -2 times 3 gives me -6. What else do I know? Well, I know hydrogen is usually +1. There's only one hydrogen. No subscript means 1. So it's +1. So now I don't have a rule for nitrogen. And when I look on the periodic table, it has a bunch of oxidation states. So I can't just use one that would be given. So I got to figure that out. So this is my one unknown. But that's not too bad. So where am I at right now? -6 and +1. So I'm at -5. So what do I need to get to 0? +5. So +5 + 1 is +6. -6, 0. All right. So now we got to distribute that +5 amongst our nitrogens, but there's only one. So it gets the whole +5. So now we're done. When every element has an oxidation state, you're done. Regardless of any polyatomic ions, every element gets an oxidation state. So now the next one, OF2. So what do we get here? Well, we know fluorine is always -1, right? So -1 times 2 gives me -2. And what do we know about oxygen? Well, we know oxygen is usually -2. But if I put a -2 in there, that's not going to work out. -2 and -2 gives me -4. It doesn't give me 0. So thinking about your rules, remember those words that we're associating with them, always and usually. So when that happens and you have a conflict, always overrides usually. So always wins. So always overrides usually. The usually is the one that's going to have to adjust to get things to work out and add up to 0, right? So oxygen's not going to be -2 here because we need it to equal +2. So there's only one oxygen, so it gets the entire +2 charge. All right. So always overrides usually. Remember this when we're talking about our general rules for applying oxidation states. So fluorine wins, and then oxygen's the one that has to adjust, and it becomes +2 in this case to get it to equal 0. All right. So now take a second, and I want you to try this one out on your own. So pause the video and see if you can assign oxidation states to all the elements in these compounds. So remember, make your little table. The whole thing's got to add up to 0, and give it a second and try it out. So pause the video and then unpause it when you're done, and we'll see how you did. Okay, so how do we do here? Well, again, use what you know to figure out what you don't know. We know K is a group 1 element. So if not, have your periodic table out, take a look at it. K is group 1, which means it's always +1. So +1 times 2 gives me a +2 total, right? So get your total on the bottom. So +1 times 2 equals +2. So remember, we're timesing on our way down, right? And oxygen is usually -2, so we're going to use that to help us out. Timesing on our way down. -2 times 7 gives me a total of -14, right? So now what do I need to get to 0? So now chlorine, I can't use -1. That only works when it's on the end of the compound. It's not on the end, it's inside. So we got to figure it out. So how do I figure it out? By seeing what I need to add up to 0. So I've got -14 and +2. So I'm at -12 right now. So I need +12 to get to 0. All right, but now you're not done. Don't forget to distribute that charge amongst the individual atoms. So there's 2 chlorines. So +12, we got to distribute that amongst the 2 chlorines. So remember, if we multiply on our way down, we're going to divide on our way back up. So +12 divided by 2 gives me +6. So chlorine gets the +6 charge, okay? So now that's what you're going to use for your oxidation state. So when you look at the periodic table, that +6 might not be on there. It's okay. Those are just common oxidation states that are in the top right corner on your periodic tables. If you get an oxidation state that's not on there, it doesn't mean that it's not possible. It's just not a common oxidation state. So don't get confused by that and think you're doing something wrong if that oxidation state is not on the periodic table. Those are common oxidation states, right? So how do you know you're done? Every element has an oxidation state. So there's 3 elements in this compound. All 3 elements need an oxidation state. So now let's look at one last thing before we do some practice problems. Well, two more things. So what about parentheses? So how do parentheses play out? So remember what parentheses mean in math. Parentheses mean to multiply. So just make sure you're getting your total number of atoms of each element when you're figuring out your oxidation states, all right? So what do I mean by that? Well, there's NO3 here. So this 3 means that there are 3 NO3s. So how many oxygens are there? 3 times 3 is 9, right? How many nitrogens are on there? 3 times 1 is 3. How many aluminums are there? Well, that 3 doesn't apply to aluminum because it's not in the parentheses. So there's only 1 aluminum. So if you want to rewrite it, feel free to rewrite it. We can write it like this. You don't really have to do that. You can just write the numbers underneath. That's generally how I like to do it. And figure things out. So again, make your table, but don't forget about your total numbers of N's and O's when you're figuring things out. So again, still got to add up to 0. But now when we're using what we know to figure out what we don't know, don't forget about your number of atoms. So oxygen is usually -2. So -2 times 9 is -18. Aluminum, again, we don't have a rule for aluminum, but when you look on your periodic table, it only has one choice, so we can use that, +3. +3 times 1 gives me +3. So now what do I need to get to 0? So what am I at? -18 plus 3 gives me -15. So I need +15 to get me to 0. So there's 3 nitrogens, so +15 divided by 3 equals +5. All right? So we're done. How do we know we're done? Every element has an oxidation state, right? So that's it. +3, +5, and -2. So every element, it's an oxidation state. So use what you know to figure out what you don't know, and there's only going to be one unknown. All right, so now the last thing. Rule number 5. So if we're dealing with a polyatomic ion, so remember, poly means many, so a many atom ion here now has a charge. That charge is given. So if you're given a compound with a charge in the top right, that's a polyatomic ion. So now this is an instance where it's not going to add up to 0. So in this case, the sum of all the oxidation numbers must equal the charge. That's not telling you oxygen's charge. It's telling you the whole thing has a charge of -2. So when we add these up, they're going to add up to -2. So when you have a polyatomic ion, the sum of all the oxidation numbers has to add up to the charge, not 0. So it's only when there's a charge there. That charge will be given. You're not adding that in. All right, so again, same thing. Use what you know to figure out what you don't know. So what do I know? I know oxygen is -2. -2 times 4 gives me a total of -8. So what do I need? Not to get to 0, but to get to -2. So if I'm at -8, what do I need to get to -2? I need +6, right? So +6 and -8 gives me -2. So it's not +8 because we only want to get to -2. All right, so if you got to use a calculator with this, feel free. So don't make mistakes because your mental math isn't the best. If you got to use a calculator here, feel free to do so to figure this out. All right, just make sure you're putting in your minus sign when you need it and whatnot, and that'll help you out. So there's only one sulfur, so it gets the entire +6. So now we're done. So that's the only difference. If it's a regular compound, it's always got to add up to 0. But now if it's a polyatomic with the charge, then it has to actually add up to the charge. That's the only time it's not going to add up to 0, if it's a polyatomic ion with a charge, right? So those are all the rules. The next thing I want you to do is to practice. So let's try these 7 problems out. All right, so before you go on and practice these, though, let's take a look at one of these together. All right, so remember what we're going to do here. Break them up by element. Doesn't matter whether it's a polyatomic ion or not. So this we're going to break up here, here, right? And the whole thing's got to add up to 0. So the whole thing's got to add up to 0. So, and again, use what you know to figure out what you don't know. So this is where your rules come in. So we know oxygen is usually -2. So -2 times 3 is -6. And what else do we know? We know hydrogen is usually +1. So +1 times 2, that gives me a total of +2. So now what do I need to get to 0? So I'm at -4. So I need +4 to get to 0. There's only one carbon, so it gets the entire +4, and we're done. All right, so how do you know when you're done? When every element has an oxidation state. So the only time they're not going to add up to 0 is if there's a charge in the top right corner. So that's telling you you're dealing with a polyatomic ion, so the whole thing has to add up to that charge. All right, so pause the video, try the other problems out, see how you did. So when you're done, check your answers. Here are the answers. We already did number 1 together, but let's go through the other ones. Number 2, right? Use what you know to figure out what you don't know. So oxygen is usually -2. So -2 times 3. Remember, we're multiplying on our way down. Gives us -6. So what do I need to get to 0? I need a +6. But now don't stop there. You got to distribute that amongst your ions. So there's 2 of them. So remember, we multiply our way down and we divide on our way back up. So +6 divided by 2 gives you +3. So now you're done. So you need the oxidation states for each individual atom. So top right numbers. You got to have a number in the top right for every element, then you can move on. Number 3, good example of how always overrides usually. Don't forget about that when we're looking at our rules. So lithium's a group 1, which is always +1. Hydrogen, our rule says it's usually +1. But if we give hydrogen a +1 here, the whole thing is going to add up to +2. So that doesn't work. So always wins. Hydrogen has to adjust, becomes -1. That gets us to 0. All right, next one, number 4, is a good practice problem that shows us the parentheses. So don't forget about what the parentheses mean. So NO3 is in those parentheses. So 2 times 3, that means we have a total of 6 oxygens and 2 nitrogens. So we only have 1 zinc because those parentheses don't apply to the zinc, right? The 2 doesn't apply to zinc because the zinc is not in the parentheses. So now let's try and figure things out. So use what you know to figure out what you don't know. So -2 times 6 is -12. And then what else do I know? Well, I can't have 2 unknowns. So I'm left with zinc and nitrogen. But don't forget, use your periodic table. If an element only has 1 charge, then use that 1 charge. So when you look on the periodic table, zinc has only 1 oxidation state, +2. So we're going to use that to help us out here. So give zinc the +2. There's only 1 zinc, so our total is +2. And then what do I need to get to 0? +10. Don't forget, there's 2 nitrogens. So now you got to distribute that amongst those 2 nitrogens. So +10 divided by 2 is +5. So now you're done. All right? 5 and 6 are reminding you to remember your rule number 1. Uncombined elements get a 0. So don't overthink these and start using the rules for compounds. Right? When it's an uncombined element, when they're all alone, they get a 0. So don't forget that. You screw that up, it's going to make a lot of problems going forward in this unit. Right? Uncombined get a 0. Even though there's 2 bromines here, this is still considered an uncombined element. So it gets a 0. Put the 0 in right there and move on. You're done. Last one, number 7. This is an example of your polyatomic ions. This is the only time it's not going to add up to 0. This is giving you that -2. It's not telling you oxygen's oxidation state, right? It's telling you the whole thing is -2. So make sure that everything adds up to -2, not 0. So oxygen is usually -2, hydrogen is usually +1, but now carbon only has to add up to +3 because that's going to get us to -2. We don't want to get to 0. So then carbon gets the +3. So when you're done, when every element has an oxidation state up top. So that's it for this lesson. If you did all 7 of these problems and you got them right and you did them well, then you're in great shape. So I'll see you next time.